Okay, I'm going to start talking about the recap just from the beginning for those of you who would like to see the overview of this chapter again up to this point. Let me go to my slide. Okay, so we talk about the radiation process. Get this thing out. Radiation process can happen even in the vacuum. Radiation process actually it volumetric phenomena, meaning every element of the subject can radiate. But in this chapter, we're gonna talk in this class. We're gonna talk as if it was the surface phenomena. Okay, so it's gonna be no radiation from the inner side of the object. The radiation going to be radiated from the surface only. Even you have a 3D object, it's going to be represented as the surface. Okay, so surface can radiate. The way it can travel through space without a medium is that the radiation, the energy transform itself into the electromagnetic wave, and then when it arrives to destination, it's turned into heat. So the whole process is called radiation. So it has to be the conversion of the energy into electromagnetic wave, and it's going to be the electromagnetic wave converted into the heat. So it maintains all kind of the properties of the wave. It has velocity, it has the wavelength, and it has the frequency. A number of frequency or wavelength can be transmitted from the subject itself. So the number of the wavelength that we have, it's so many. We call the property as the spectral. Okay. So we talk about the direction of the distribution too. For example, this is a surface, and one point on the surface itself, it can radiate, sending out energy in many directions. To say the truth, it is in every direction upward into the surrounding with our medium, and the amount of the radiation can be varied. It can be maximum, it can be minimum, maximum in this direction, minimum in that direction. It can vary. Okay, it can vary in terms of wavelength too. See, the intensity of the radiation is on the y-axis, and the wavelength is on the x-axis, so it can vary. Okay, and we define the radiation intensity. This is the emission. When you have a surface and it is at the temperature as Ts, and the Ts greater than 0 Kelvin, it always radiates the energy out. Okay, we would like to measure that energy. That energy we call emission. Okay, so we specify what so-called the radiation intensity, which is the has a unit of watt per meter square per 3D 3D angle, which we call sterradian, and per wavelength. Okay, so when we make the integration over the intensity, for example, this is the intensity. We make the integration in every direction. This is a concept that we talk about it last time. This is the integration of intensity. Integration of intensity to make it, to sum it actually. To sum our intensity in every direction. If we do the integration like so, what we're gonna have, it's not just intensity in one direction or in one wavelength, but it's gonna be in every direction. This is energy emitted in every direction. Okay, but still, the energy that we carry out from the integration is going to be specified at 1 lambda. Okay, if you want to make the integration once more, you can take this the energy in one wavelength to be under the another integration. Now it's going to be integration from 0 to infinity of lambda, meaning that you can study the radiation of the energy in terms of emission from 0 to infinite wavelength, include all the wavelength. This is energy in every direction and every wavelength. Okay, so you're gonna have the, so the equation which is important would be this equation. Okay. And we talk about the, for the diffusive emitter, that's the another whole concept. I would not go into the detail because we already talked about it last time. This is a quick recap. Another phenomenon in addition to emission, it's radiation. We use the concept G, the symbol G, okay? And we use the G lambda, meaning that it is a radiation onto object at one particular wavelength. What is the radiation again? Okay, if you have a surface and the surface itself is TS, of course you can have emission, okay? But the surrounding or another object, the other object gonna have the emission too. And part of the emission gonna arrive to the surface TS, and this is G. Okay, you can study the radiation arriving to the object in terms of G, which is the radiation in every direction in every wavelength, or G lambda. G lambda is the radiation in one wavelength. Right? But G is every wavelength. Okay, so the important equation would be that. Okay. And then we talk about radiosity. We use symbol J, and we have J lambda. Similarly, it is the quantity measured at one wavelength, and we have a J. J is the quantity measured in every wavelength and in every direction. What is radiosity again? Radiosity is in terms of radiant energy leaving a surface. So when you have the emission, because of the temperature Ts, you got the emission out like that. You're gonna have also the radiation coming in, and it's gonna be reflected. Okay, so we call the summation of these two, emission and radiosity. I'm sorry. I should turn off his mic first. We're gonna have the radiation and it's gonna be reflected. Okay, so part of the summation of emission and reflected, we call it radiosity. Okay, and as you might guess, the important equation would be something like that. So in conclusion, emission can be found from this equation. Radiation can be found from this equation. Radiosity can be found from this equation. Okay? And then we get back to the item E. This is the emission intensity. Because when you have a surface and the surface itself is at temperature Ts, and you need to find the emission intensity, okay, in order to find how much the emission it is, using this emission intensity in order to find the whole emission, or at least you would like to find E lambda. Okay, so I give you the radiation of black body, the radiation of black body, because the black body itself is the ideal material. It can absorb all the incident or the radiation, all of them, 100% of the radiation onto it. It can absorb all of them in every direction, in every wavelength. And when you talk about the emission, if you have two body, one is black, one is real, and they are at the same temperature. When you measure the emission out of these two, the emission from the black body would be the most. No real body can emit energy more than the black body if they are at the same temperature. Okay? No surface can emit more energy than black body. Black body is diffuse emitter. What does diffuse mean? Diffuse. If you have a surface and you use the arrow in terms of intensity, this is 90 degree. The other degree is going to emit the energy equally. So the way it emits the energy is kind of hemispherical shape. Okay, so the if it's emit the energy equally in every direction, we call it diffuse. Okay. So for the black body, I lambda B, lambda E is called I lambda B. We change the subscript of E into B in order to signify that this is the emission intensity for the black body, okay? And the equation is given in something like that, okay? This is for black body. And if you want to find the E lambda, okay, for the black body, you just plug this thing inside here. And for black body, you can write E lambda in terms of E lambda B. We put the we put extra subscript over there, okay, to put B in, meaning this is the energy in one wavelength, emission in one wavelength for the black body. So this is the equation after the integration is over. This equation becomes this, okay? And because you know, if you want E is integral from 0 to infinity of E lambda d lambda. So for black body, EB, we're going to call E for black body by putting subscript B in, meaning this is this belong to the black body. It's equal to integral of, you put something like this into here and make the integration. After the integration, this is what you have. Okay, so EB equal to sigma T to the fourth. Okay, and then we define, the ratio of emission from wavelength 0 to lambda. Okay, so meaning that we're going to find the amount of energy from 0 to infinity of E lambda B. Basically, this is EB, but you don't make the integration from 0 to infinity. What does it mean anyway? It's the part of emission from lambda equal to 0 and lambda equal to the amount that you specify. In comparison, if you compare it in comparison with the same integral, but from 0 to infinity of E lambda B, this is what? This is the whole energy, whole emission in every wavelength. On the top is part of emission from wavelength 0 to some lambda. So if you compare this ratio, and we call it black body radiation function, F0 to lambda, okay? Because the on the bottom is equal to lambda T to the fourth. On the top, okay, it is the integral. You can take the sigma T to the fourth inside the integral, because this is the constant. Then if you want to find this ratio, you don't bother to make your calculation by yourself. It's already tabulated. Okay, so this is the table to find F0 to lambda. Okay, and all you need to know lambda and you need to know T. You find the product between these two, and see where you are. If you are here, okay, you can read the F0 to lambda right away, okay? And it's happened that, let me write it down. Oops. Ah, sorry about that. Okay. So because the fact that when you draw the F0 to lambda, it is the integral from 0 to lambda of E lambda B d lambda over sigma t to the 4. Now, basically it is the on the top, here. It is the integral of E lambda b over sigma t to the 4. This is the lambda. Okay, if you have a property and there is the characteristic of E lambda b over sigma t to the 4 as the graph, as shown in the sketch in front of you right now. Okay, so this integral, meaning it is the finding the area under this curve. Okay. Sometimes if you would like to find, if you want if you want to find the f from lambda 1 to lambda 2, okay, meaning that you need a portion of the integral of lambda 1 to lambda 2 of E lambda b d lambda over sigma t to the 4. If you want to do that, meaning you're trying to find this portion, lambda 1 to lambda 2. How do you make the indication like so? So you can do that by finding that the f lambda 1 to lambda 2 equal to f 0 to lambda 2, meaning that you find the area. Let me make a color code over here. Just green from 0 to lambda 2, okay? And then minus, I need the violet here, f from 0 to lambda 1, because remember, you want the blue area underneath the graph, but how do you find it? You need the green area first. Where is the green area again? Green area is from here to there. Okay, from 0 to lambda 2. Minus the violet one, the pink one, from 0 to lambda 1. Where is the area again? Area is here. Oh, I'm sorry. Here. So the green area minus the violet and the pink area, what remain, it is the blue area. Is that what you want? Okay. So that's the concept of radiation function. Okay, we are coming to the example that you probably have in the book. It's called the emission radiation from the light bulb. It gives the temperature of the filament of the light bulb, okay? And it gives the temperature of 2500 Kelvin. And you treat the filament as the black body. They would like to find the fraction of radiation energy emitted by that filament. And that's for on the visible range. So they need the F from lambda 1 to lambda 2. This is for visible range. And visible range is starting from 0.4 to 0.7 micrometer. So if you have a graph like that, take a look at the graph on the bottom. The y-axis is EB lambda over EB. Note EB equal to sigma t to the fourth, okay? And this is 0.4, this is 0.7, and you need the area, okay? So you need to find F 0.4 to 0.7 equal to F 0 to 0.7 minus F from 0 to 0.4, okay? So in order to find these two, you need to find lambda 1t for ts first, and you need to find lambda 2 ts. I'm sorry, this is the lambda 2 ts, and this is lambda 1 ts. So lambda 1 equal to 0.4 micrometer, lambda 2 equal to 0.7 micrometer, right? So they do it. Lambda 1 equal to 0.4 multiplied by 2500. This is what you have. And you use table. You read the fraction equal to 0.000321. And you find lambda 2, okay? And lambda 2t multiplied by t equal to 1900, and the fraction is equal to 0.053035. And once again, you plug this thing in here and there, and you got the fraction. So the emission from the filament would be visible into your eyes just only a little bit above 5%. Okay. And they asked us to find the wavelength at which the emission of radiation from the filament peak, meaning where is this one? Okay, this is peak. I'm sorry, this one keep peak, and they asked lambda equal to what? We're going to call it lambda max. In order to find a lambda max, it has the Weir equation, relation, which okay, this is Weir displacement law. In Weir displacement law, you just plug t in over here in order to get the lambda max, okay? See, 3 is a constant. So that is the example, okay? And then if you take a look at the get back to the radiation of black body again. We talk about emission intensity, but this intensity gonna give you just only for black body. How about the real body? How do you find the emission from the real body? Okay, that's how we start from here. Radiation from the real surface. You need to find, you want to find the emission. E or E lambda, that's fine. Okay. Last time when we talked about this thing, we starting it off with identifying the another intensity. Okay. We call the not intensity, property. Okay. We call the property emissivity. Okay. And you compare the emissivity is the property to emit the energy. Ability to emit energy over the same ability to emit energy if the object is black. Okay? So when you have the emission epsilon, okay, and you put the subscript lambda and theta in, it means the ability to emit energy in one wavelength and one direction. So when you compare it, you compare the intensity of the real body and the intensity of the black body together. Okay, if you you can study the emissivity, and you put lambda over here. This is the ability to emit energy in one wavelength, but in every direction. Okay, so when you compare that, you have to compare E lambda, okay, over E lambda B, okay? And then if you want to find the just the epsilon, this is epsilon, it has no subscript. This is the, you want to compare the emission of the real body over the black body, okay? And in every wavelength and every direction. So from this equation, it's comparison between E over EB. So you know that EB equal to sigma T to the fourth. If you want E, E is just epsilon multiplied by EB, meaning that it's epsilon multiplied by sigma T to the fourth. So, in conclusion, okay, this is important. By definition, you already know that E equal to integral of, let's say, because E lambda equal to epsilon lambda multiplied by E lambda B. How do we get this? Okay, from the last slide. Okay, over here. This equation can be written as E lambda equal to epsilon lambda multiplied by E lambda B. Okay. Remember this expression, and then the same thing. Okay. Because we know that E equal to integral of 0 to infinity of E lambda d lambda. So I just plug this thing in here. Okay. And I know that E equal to this, and I put it in here. This is what I have over. This one is sigma t to the 4. Okay, so my epsilon once again is equal to integral of 0 to infinity of epsilon lambda e lambda b d lambda over sigma t to the 4. Okay, if you ask me which one is important, okay, the important part is this equation. You have to understand this point, okay? Then, basically, if you talk about epsilon most of the time depend on the wavelength. For example, if you take a look at this plot on the y-axis, it is the E lambda, okay? And they put the subscript E lambda n, mean. This is mean in normal direction, meaning if you have the surface over here, this is the radiation in this direction, 90 degree to the surface. And this is the radiation in terms of wavelength. Okay. So the amount of the emission vary in one substance. For example, this is a substance of the stainless steel. Okay. It emits energy in 90 degree in every wavelength. This wavelength 0.4, this wavelength 0.7, this is visible range, so they're not equal, okay? But typical surface, we're gonna hold epsilon approximately equal to epsilon n, no matter it's vary, okay? You can browse into the back of the book in order to check out for the epsilon for each material. Make sure that you know how to get the number out of the appendix in terms of the epsilon, okay? Well, now it's going to be just the example of what you have in the book. It's a spectral emissivity function of the opaque surface temperature at the 800 degree. It is approximated like that. So it has the three ladder plot. On the y-axis, it is the epsilon lambda. On the x-axis, it's the lambda. And it has the stepping plot like that. Okay, this is part 3, this is part 8, and this is the part 1. So then they ask you to find the epsilon, okay? And it also asks you to find the emission. This is the emissivity. So the emissivity by the equation, take a look at the equation. Okay. The emission is something like this equation. Okay. So in order to find that, let's get back to that page. Okay. So you need to find the epsilon. Epsilon is integral from 0 to infinity of epsilon lambda multiplied by uh, e lambda b and d lambda over sigma t to the fourth. Okay. So you have meaning that you have to find the products. What I mean by product of this thing. Okay. But the integration would be range 1, range 2, range 3. Okay, so you started out with breaking the integration into 3 regions. Epsilon going to be equal to, for the first region, okay, the epsilon is constant as part 3. You can take the part 3 out from indigo, something like that, okay? Epsilon 1 multiplied by integral of 0 to lambda 1 e lambda b d lambda over sigma t to the fourth, and do the same thing for the second region and the third region. Okay, and if you look at the first region, for instance, epsilon equal to epsilon 1 integral from 0 to lambda 1 e lambda b d lambda sigma t to the fourth plus epsilon 2 because it's constant 2 from lambda 1 to lambda 2 and e lambda b d lambda over sigma t to the fourth plus epsilon 3 integral of lambda 1 to lambda 3 lambda 2 to lambda 3 and e lambda b d lambda over sigma t to the fourth. Okay, you know that this thing is part 3, this thing is part 8, this thing is point 1. Okay, so the integration of the first one you have to find this. Okay, this is nothing, it just multiplied by f0 to part to lambda 1. Lambda 1 is the 3 micrometer. Okay, plus this one is 0.8. 0.8, this is the f from 3 to the number is 7. Okay, plus 0.1 f, this is from 7 to infinity. You have no problem with this. Okay, just table. And if you take it from the table, it is the 0.140, okay? And plus, then this is, you need to take the, do the same thing as previously that I showed you. This is 0.770, 1 minus 0.140. And this is the 0.1 multiplied by this piece. This piece, well, if you make the integration from 0 to infinity, it's going to be equal to 1. Okay, let me note it here. If you make the integration let's say, I should say f from 0 to infinity equal to 1. Okay, you want to find f7 to infinity equal to what? So I would say it is equal to 7 to infinity equal to 1 minus f0 to 7. Okay, so and what they have, this is the 1 minus 0.701. Okay, take a look. Here, here, and there. 1 minus 0.701. Okay, and you're going to get the epsilon equal to 0.521. And they asked you to find the emission once again. Emission, let me clean it up first. Okay, so emission is something like epsilon multiplied by sigma t to the 4th. Why is that? Because epsilon is equal to E over EB. And EB is sigma t to the 4th. Okay, I just rearranged the equation. So my epsilon, I already know it is the 0.521 temp. I already know at 100 Kelvin. Remember, this should be in Kelvin. Okay, if it's given in Fahrenheit, if it's given in the Celsius, you have to convert it into Kelvin first. So you're gonna get E. Okay, substitution gonna give you E equal to 12,100 watt per meter square. Right? So that's the example. Now we're gonna step up and talk about the more on the ability, more properties. The property connected with the phenomena is the phenomena of absorption, reflection, and transmission. Okay, if you have the subject, okay, or the object of interest, doesn't matter it is the 3D matter, how it look like, how it looks like, but we represent it by the surface. Represented by surface. So this is the surface, okay, and basically it's like the glass. Okay, and the phenomenon is something like this. You're gonna have the radiation coming in. And once it arrives to the surface, it has three choices. The first choice is get reflected. Second choice, absorb. Third choice, transmitted. Okay? If the radiation coming in terms of G lambda, what is G lambda again? G is a radiation. Let me remind the unit of G. Unit of G is watt per meter square. And we put the lambda as a subscript, meaning that it is the energy in one wavelength only. Once it's arrived to the surface and got reflected, part of it is going to be reflected by G lambda reflected, okay? And transmit G lambda transmit. and absorb G lambda ABS. So if you take the energy balance of the system, it's going to be G lambda equal to G lambda reference plus G lambda absolute absorb plus G lambda transmit. And you can divide the both side by G lambda. You get 1 on the left-hand side, and you have the G lambda reference over G lambda absolute by G lambda, and G lambda transmission over G lambda. We have 3 property now, because each of the comparison telling how much the object can reflect, how good the object can absorb, how good the object can transmit. Okay, we're gonna call each of them as the properties. The first one, we call it reflectivity. The second one we call absorptivity. The third one we call transmissivity. Okay, and it all has a subscript lambda. It means it is the property which is spectral, meaning it depending on 1 lambda, and hemispherical, meaning in every direction. Okay, spectral mean 1 lambda, hemispherical mean in every direction. Okay, the same thing. If I redo the pictures again, incoming, it's not G lambda, transmit, it's gonna change too. If I talk about irradiation as G meaning the irradiation in every wavelength and in every direction. Okay, so it's going to be reflect, G reflect. It's going to be absorb, G absorb. It's going to be transmit, G TR. So G, take a look at the equation down there. G going to be equal to G reflect, G absorb, G transmit, divided by G on both sides. You're going to have each ratio, and each ratio, we're going to call this thing lambda, we're going to call this thing alpha, we're going to call this thing tau, unlike the previous one. Comparison with the previous one, this is for the spectral and hemispheric. This is for total. Total means every wavelength, every direction, okay? If the object is opaque, meaning no transmission, G lambda transmission equal to 0, G transmission equal to 0, tau should be equal to 0. So what remains is going to be G lambda and, rho lambda plus alpha lambda equal to 1, because tau lambda equal to 0. Likewise, the rho plus lambda alpha equal to 1. So that's the concept. Then we're going to talk about absorptivity. Now that you know that it is, you can find G lambda, you should know G. Absorptivity alpha and alpha lambda and alpha. Okay. You would like to find the property alpha lambda and also alpha. So what is it again? Well, for hemispherical absorptivity, you need to find the G lambda absorption over G lambda of radiation, right? So it's starting from having the spectral directional absorptivity, meaning that we're gonna have to define from the beginning lambda alpha of lambda and theta. This is absorptivity at 1 lambda and 1 direction. How do you find that? This property, comparison with the intensity. But intensity in 1 direction and 1 wavelength, which is get absorbed over the incident of all radiation. Okay, if I rewrite this equation, let me get it in red. Okay, I lambda I ABS is going to be equal to alpha lambda theta multiplied by I lambda I. I'm sorry. I lambda I. Okay, so this is the intensity in 1 direction, in 1 wavelength. So if I put this thing and make the integration twice, in comparison with respective to cos theta, sin theta, d theta, and d phi, I'm going to have this equal to g lambda. Okay, and the over here is going to be the same. It's going to be the radiation at one wavelength. Let me clean it up first. Okay. So I redo it again for this equation. This equation, I know that G lambda that get absorbed equal to alpha lambda multiplied by G lambda. Okay. In this case, for alpha, I need the G absorbed. This is in every wavelength. How do you find that? Okay, G absolute absorption is equal to infinity of G lambda ABS and D lambda. But we know that this thing equal to this. I plug it in here. I know G abs is equal to 0 and alpha lambda, G lambda, D lambda. Okay, it just plugged everything in here. So after that, I put this thing in here. Okay, this is what I have. Okay, if you ask me which part of this page is important, which part that I should know, I'm going to give you just only one equation to remember by. So that equation would be this. Okay. If you do the same thing for the reflection and also the transmission, I will go quick on this. Okay, you're gonna get the make the comparison. This I put this one at 1 star. Oops. What happened? I'm sorry, my pen wouldn't work anymore. Okay. Okay, the important part is this equation and that equation. Okay, you follow the footstep once again for the reflection, what you're gonna have with this equation and that equation. Okay, and you follow the footstep for the transmissivity, you're gonna get this one, and that one. So three set of equation, they look similar, but not the same. Okay, but the way we derive it, it has in the same manners. Okay, so right now, your ability would be ability to find epsilon, rho, alpha, and tau. Okay? So epsilon would be, you make the integral of 0 to infinity of epsilon lambda and E lambda B. Let me write it down here for you. This is D lambda over sigma T to the fourth. Okay? And you know how to find alpha. Alpha is integral of infinity, 0 to infinity of alpha lambda and G lambda, D lambda over integral of 0 to infinity of G lambda, D lambda. Okay, rho, well, you write the equation in similar to that, you're gonna get lambda lambda, G lambda, rho lambda, G lambda, D lambda over integral of 0 to infinity of G lambda, D lambda, and tau equal to. If you ask me what kind of the equation which is important to this portion of the chapter, this is the four important part. Okay? 1, 2, 3, and 4. Okay? Okay, guys, I know that time is running out, but as I was saying, this class is recorded. Okay? I'm gonna continue to talk, and probably I'm gonna end at a little bit after 10 o'clock. But if you have another class or if you have anything to attend, you can leave the class. But I will post my lecture once again tonight. Everything is recorded, so we'll post tonight. Okay? So I will tell you where to get the file tonight. So if anybody once again have something to deal with, you can leave the class right now to attend what you have to do. But if you don't, you are invited to continue to hear my lecture. Otherwise, wait for tonight file MP4 will be posted. Okay. And in the book, there will be the graph showing each of the property, just saying that it's depending on wavelength. All the property, most of the time, depending on wavelength. Okay, see the wavelength, and this is the tau lambda, and this is flow lambda, and this is wavelength. So graph is not straight line like that. It's wavy like that, meaning it's not constant. Okay, line like that. It's not constant at all. That's the concept, just to show you how much, how dependent the property on the wavelength. Okay. Well, bring me to the next concept. The next concept is on the Kirchhoff law. What is the Kirchhoff law? It's the law. At the end, you're gonna have the conclusion that alpha lambda is going to be equal to epsilon lambda. Spectral absorptivity is going to be equal to spectral emissivity. And also, absorptivity is going to be equal to emissivity. And in what condition? Okay, well, it's a condition where you have the enclosure large. When you say you have the enclosure, it doesn't mean you always have just only a tank, okay? A tank, something like that. What inside the tank? You have blue thing inside the tank, and it's contained by the tank itself, okay? The tank to the blue dot, it is the enclosure. However, if you are people stand, okay, on the ground, and above you it's nothing, it's just the sky, okay? However, if you talk about it, then take a look at the geometry of what you're standing. It's not like a tank. This is a tank. This is the obvious enclosure because it is a tank, right? It's so obvious. But when you stand on the ground and you're surrounded by the sky, if you're standing in the nighttime, the sky is so black and around you is so black. When it's so black and the temperature would be something like 2 Kelvin, it seems that everything around you which is black is at temperature of 2 °C. It's as if you were covered by the tent of black sky and probably low temperature at 273 Kelvin. So this is also enclosure. So enclosure is not a house, it's not a box, it's not just only the car that you are in. It also, sometimes it contains the sky too, okay? So most of the time, once you are in this world, you are in the enclosure. It's the enclosure of the sky. Why the sky is the enclosure? Because it has it has the same temperature. If the sky around you has the same temperature, they are covering you with that temperature. So it is the enclosure. Okay? Let me clean it out. Okay. So our question will be emphasized again. We know that this is the Kirchhoff law, but in what condition? So you're going to have the large enclosure first. Okay? Let's say you have so many objects inside the enclosure. Let's call it A1, A2, A3. Let me emphasize again, there are so many objects inside, but we're going to represent it by surface. Right? Why? Because the radiation phenomena is studied in terms of surface phenomena in this class. So let's say we have A1, we have A2, we have A3, we have 8 until AN, possibly, inside the enclosure. So the surrounding the enclosure itself is at the temperature Ts, and let's say the object is at some temperature too. Okay, they are all in equilibrium. Okay, when they are in equilibrium, the enclosure itself emits the energy out. When that energy arrived to the each of the object, it become a radiation at that object. Can we find the emission out of the enclosure? Of course, if the enclosure is large, okay, it can be considered as the black body at the TS. Okay, so a radiation from the surrounding onto the object we can calculate. It is equal to EB, G equal to EB, because the surrounding is black. Okay, so if the object is in equilibrium, let's take a look at each object. Each object, let's say A1. And the part of the radiation onto the object is G1. Okay, if you have A2, part of the object would be radiation would be G2. If you have A3, okay, radiation would be G3. In fact, G equal to G1 plus G2 plus G3, depending on how many objects that you have. Right? So if you take a look at the first object, you multiply G1 with A, you're going to have a radiation. And once you have the irradiation onto A1 tend to increase its energy, right? So it's not in equilibrium. In order to get into equilibrium, they have to emit energy out. So they have to emit E1. So we equate the irradiation with emission. Okay, you're gonna have G1 multiplied by A1 equal to E1 multiplied by A1. Okay, G and E has the same unit, watt per meter square. How do you find G1 once again? G1, we already know that alpha 1 equal to G1 over G. This is from the last topic that we just left. Okay, so we rewrite this equation. You're gonna have G1 going to be equal to alpha 1G. So I put G1 equal to alpha 1G over here, okay? And then we rewrite this equation. A1 cross A1 out, so G going to be equal to E1 over alpha 1, okay? So we do the same for the A2. We're going to have G equal to E2 over alpha 2. We do the same for E3, A3, the area 3. G going to be equal to E3 over alpha 3. Okay, so this is my summary. E1 over alpha 1 equal to E2 alpha 2 equal to EB. Okay, and E1, what is it? Well, we know that epsilon 1 going to be equal to E1 over EB. So this thing is going to be equal to E1, I'm sorry, it's going to be equal to epsilon 1 multiplied by EB1. This is epsilon 2 multiplied by EB2 and so on, okay? And EB is going to get canceled on both sides. So this is what you're going to have, okay? So epsilon 1 going to be over alpha 1 going to be equal to 1. Epsilon 2 over alpha 2 going to be equal to 1, giving you epsilon 1 equal to alpha 1. Epsilon 2 equal to alpha 2. Okay? So in general, in general. In general, you can say that in enclosure, epsilon is going to be equal to alpha. Okay. So let me erase everything here real quick. Okay. So in what condition? In enclosure. Okay, in equilibrium enclosure. So what's next? You can do it the same by starting off with G lambda, and this thing gonna emit E lambda 1. Okay, and you can make a proof that epsilon lambda gonna be equal to alpha lambda 2. Okay, but I'm not gonna repeat it myself. It has the same concept, but take a look at the irradiation in terms of spectral in one wavelength. So it's gonna be the same. Move to the next slide, like that. You can go on in epsilon lambda theta, it means that in one direction. This is for one direction and one wavelength. This is the every direction and one wavelength. All right. And also you have to take a look at the, it has to be diffuse radiation too. The surface itself has to be diffuse, directional independent, wavelength independent, and this one is called epsilon going to be equal to alpha when the body is gray, diffuse, and wavelength independent. So going back to the previous slide, okay. In what condition? I'm sorry, my pen doesn't work. I don't know why. I'm sorry about that. Okay. In what condition? It has to be inside the enclosure and the object has to be gray surface. Okay. When you talk about gray surface, what is it again? It's diffuse and wavelength independent. Okay, that's the Kirchhoff law. Okay, that's the lecture for today. I tried to make a post tonight, and if I can, I probably make a post of the next lecture too, depending on how much time they can find tonight. I tried to complete everything by Wednesday, or at least try to put the teaching file MP4 starting this lecture section online tonight, starting tonight. All right, so you can either join my class once more on Wednesday, uh, of trying to follow what you missed once again, even if you were in the class but you want to study again. So right now you probably can do so by having my MP4 file. I will make it available tonight. Okay. So I will see you guys on Wednesday. Some you already turned in the homework. The homework is with me right now. I think you turn it in both in the email group and also into the e-learning group. That's fine. Okay, that's redundant, but it's safe. Okay, see you guys on Wednesday. I'm off right now.